Hi students, welcome back. Today we are going to solve another interesting programming problem called the balanced binary tree. Let's head to the problem statement. So the problem statement says we are given a binary tree and we have to determine if it is a height balanced or not. So that means we have to return true if it's a height balanced tree and false otherwise. So what is the definition of a height balanced tree? A binary tree is called height balanced tree if two subtrees of every node never differ by more than one, which means the height of the two subtrees should not be more than the difference between height of the two subtrees should not be more than one. Let's look at it using an example. So here we are at node 3. So if we look from 3, what is the height of the left subtree? 1. What is the height of the right subtree? 2. So they differ only by 1. So from this point it is a balanced tree. Here it is 0, right is 0. So difference is 0. Here left is 1, right is 1. Here as well left and right are 0. So at every point the difference is maximum is 1. So this one is a balanced tree. Whereas if we look at another example, here if you see left is 2, no, left is 3 and right is 1. Okay, rest of them are same as previous example. Only at this point it is differing and the difference is 2 which is greater than 1. Hence, this is not a balanced tree. So one thing if you observe, we have to check for height at every node because even though it is not guaranteed that if root is balanced, that means every subtree is balanced. Okay. So we have to check at every node and figure out if it's a balanced or not. For example, if a tree is like this, okay. Okay, if you check just from the root, it is a balanced tree. 3 minus 3 is 0. But if you check here, the height of this node is 2 and it has no right children. So here left is 2, right is 0. Difference is 2, which is greater than 1. Hence, this tree is also not a balanced tree, which is why we should check at every node. Okay. So checking for it at every node using the normal height algorithm will be order of n square. So let's look at a more optimal solution. Okay, there is another example. If the tree is empty, then it is always true. It is always balanced. Okay. So our algorithm would be an improvement on the finding the height of the binary tree. So first let's write the height algorithm. How do we find height? We take root as input, okay, and if root is null, that means it is an empty thing, then height is 0. Okay, so this is the base condition. Now if that is not the case, then we get the left height which is recursively going through the tree to the left side. Okay, and we get the right height which is again recursively going to the right. Okay, so at this point we have both left and right height, and height of the tree would be max of left height and right height. So height of left side and height of right side, max of one of them plus 1, because we are looking at the height of the parent of these two things, right? That is why plus 1. So this is our height algorithm. So what we will do is, instead of just returning the height, while computing the height, we will also figure out if the binary tree is balanced or not. For example, at this point, we know that the okay. At this point, we have the height of left and right subtree. So, by going by the definition of the height balanced binary tree, what we can do is, if the absolute difference between left and right is greater than 1, that means this tree is not balanced. If one part of the tree is not balanced, the entire tree is not balanced. So, we can just return. We need not do further computation. Okay. So this is one optimization we can do, and the other one is if one of the tree returns -1, that means no further computation is required, right? So we can just return. That is here, for example, let's say left tree, which is this thing, return -1. Then we can just return -1. There is no point in computing right and absolute difference and all that. So what we can do is here, if left is -1, return. Okay. Similarly, if right is -1, we return. So the algorithm is, if we compute the height of the left tree, if left is -1, that means the left side of the tree is not balanced, then this whole tree is not balanced, we return. If the right, then we compute the right side. If the right is not balanced, then we return. If both of them are balanced, then we compute the absolute difference of it, and if it is greater than 1, we return -1. Otherwise, we return the height of the tree. So the caller of this function, which is our actual problem, what we should do is, we call this height function with the given root, and if the return value is not equal to -1, then that is a balanced binary tree. Not equal to -1 meaning it returned the height of the tree, right? We return the height of the tree only if it is a balanced tree, which is why we have to use that condition. So let's go over it through an example. Let's say we are at 1. Okay. So when we are at 1, when we go through our algorithm, is 1 null? No. So we just go to the left side. When we go to the left, we reach 2. At 2, again, we try to compute the height. So at this point, it is simply pointing to 2 nulls, right? So it goes to its left, which is null, and it returns back with height 0. Okay. Similarly, its right pointer also returns with height 0. So for it, left and right is height 0. So the height of this one would be 1. So this returns here with a 1. Now we have reached root. Now at any point we didn't see here 0 minus 0 is not greater than 1. So we don't return -1. Here we went to the root. Now let's see what happens on the right side. We go to 3. 3 goes to its leftmost node. Here again it will go to 2 children which are nulls, and the height of 4 is 0. So this one returns 1. Similarly, it goes to 5 and it returns with 1. So here 1 minus 1 is 0, which is not greater than 1. So it continues its computation and it returns 1 here. So it has 1 from left tree, 1 from right tree. Sorry, it returns 2 here because 1 plus 1. It has 1 from left tree, 2 from right tree. 2 minus 1 is 1, which is greater than or less than or equal to 1, which is why this is a balanced, height balanced binary tree. Okay, let's look at another example. So if we take this example now, so similarly, when we are at root, we keep going till we reach the end of the left node. So at this point, this one returns height as 0. It is balanced at that point. So to its parent, it returns height 1. Okay. Similarly, at this node, it goes to right as well, and it gets the response that height is 1. Okay. At this point, it has left 1, right 1. So difference is 0. So it will return max of left comma right, which is max of 1 comma 1, which is 1 plus 1. So it will return 2 here. Okay. This one again, it goes to check for the right node, and here the answer is 1 because it has no children. Okay. So at node 2, the height would be max of 2 comma 1. So here left is 2, right is 1. So max of 2 comma 1 is 2 plus 1, which is 3. Okay. Here again, before returning, we check that condition, right? 2 minus 1, 1. 1 is less than or equal to 1, which is why it will return max of 2 comma 1 plus 1, which is 3. Okay, so it returns 3 here. Similarly, it goes and checks its right children. The right children responds saying my height is 1. So at this point, it has height of left 3 as 3 and height of right 3 as 1. 3 minus 1 is 2. 2 is not less than or equal to 1. Hence, this is not a balanced binary tree. Okay. So at every point, we have to check for the left height, we have to check for the right height, and we also have to check if left minus right is greater than or equal to 1. If it is greater than or equal to 1, it's not a balanced binary tree, we can return immediately. Now, let's try to code our algorithm. So, first let's write our height function. Okay, int height. So, we are returning height only if it's balanced. So, I'm just giving a meaningful name, that's all. Okay, so what do we do in height? If first the base condition is if root is null, return 0. So if there is no elements, then height is 0. Else, and left equal to height of left tree is equal to root dot left. We call the same function with the left. And if left equal to minus 1, in case it returns minus 1, then there is no point calculating the right. We just return minus 1. Otherwise, we check for the height of right tree. Okay. And again same condition. If right equal to minus 1, we return minus 1. Okay. So now both of them are not minus. Then what do? We take the absolute difference of left comma right, and if it is greater than 1, then we return minus 1. Okay. So math.absolute is a inbuilt function which does the absolute value for us. So now even this didn't happen. That means the tree is balanced, which means we have to return the normal height. Normal height is max of left comma right, whatever is max, and plus 1. Okay, again math.max is an inbuilt function. Now we have to use this function. We have to call this on our tree. Okay, and if it doesn't return minus 1, okay, then it is a balanced tree. If it is if it returns minus 1 if it is not balanced, otherwise it returns a height right, which would be greater than minus 1 for sure. So this is our condition. Okay, let's run it and see. Okay, absolute of left comma right greater than 1. Therefore, okay. So math.absolute only returns the absolute value of a function. It doesn't do the difference, right? That is the error here. So here we have to do minus math.absolute value of left minus right. It basically, if it's negative, it returns positive. If it's positive, it returns the same value. Okay, let's run this. Okay, let's submit and see. Yeah, so it ran fine. It ran all the test cases fine. So what is the time complexity of this method? Time complexity is same as the height algorithm, which is order of n. We just made some optimizations like line number 30, 26 and 28 to the height algorithm. Okay, and the space complexity, again space complexity is also same as height, which is order of n. Order of n because it is a recursive one and there will be stack trace. Okay, so this is a very interesting application of height algorithm. which basically gave us an optimal solution. So this way we should be able to apply what we have learned in solving new problems. Okay, if you have any questions, please do leave a comment. Like always, keep practicing and improving your problem solving skills. Happy coding! See you in the next video.